Welcome back to the ma161 calculus. My name is Götz Pfeiffer and this video is about antiderivatives. So what's an antiderivative? Well, consider this question. Can you tell the position of a moving particle from its velocity? What we've done so far was asking the question backwards. Can you find the velocity of a function if you know the velocity of a particle if you know the position function of the particle? And in calculus terms, the velocity is the derivative of the position. So if we know the position function, we can determine the velocity. This question goes in the opposite direction. Given the velocity, can you tell the position? And intuitively, this should be clear. If you know the position at a point in time, and then from then on have a function, a velocity function that describes the development of the behavior of the velocity over time, it should clearly be possible to keep track of the position of the particle. And that's what antiderivatives are about. So we call a function capital F an antiderivative of a function little f over an interval capital I if the derivative of capital F at x is the value of little f of x for all x in the interval. So, for example, if little f of x is x squared, then a moment's thought, power rule in mind, gives us something with x cubed as an antiderivative, and to get the scalar right, the 1/3 of x cubed obviously has derivative x squared, so that's an antiderivative of little f. But then 1/3 of x cubed plus 17 is another function that has the property that its derivative is x squared. So there's plenty, and here in the diagram I exhibit a few antiderivatives of x squared. They're all of the form x cubed over 3 plus some constant or minus some number. They all have like shape in common. The only thing they differ by is their height here on in the xy plane. Obviously, the common shape comes from the fact that they have the same derivative, and in fact, it's a consequence of the mean value theorem that we saw last week, that whenever two functions, say capital F and capital G, have the same derivative, if they're antiderivatives of the same function little f, then they differ by a constant. Or one function is the other plus a constant. So antiderivatives aren't unique like the derivatives are, but they only differ by a constant, and so in that sense they are unique. They're easy to describe. And as a matter of fact, any of the differentiation formulas that we saw on the way, be it of a general nature or a formula that gives the derivative of a specific function, when you read it backwards, it gives a formula for antiderivatives. So if we use this notation as before, the derivative of the capital F is little f, derivative of capital G is little g, then we had, what did we have? The derivative of a constant multiple of a function is the constant multiple of that derivative. And now when we read this backward, the antiderivative of the constant multiple c times little f is that constant multiple c times the antiderivative of f. Or this one now, the derivative of a sum is the sum of the derivatives we had at the time. Reading it backwards, the antiderivative of a sum of little f and little g is the sum of capital F and capital G, the antiderivatives of f and g. The antiderivative of a sum is the sum of the antiderivatives. And so we can turn all differentiation formulas, most of them inside out, to find a formula for antiderivatives. The power rule, for example. And the derivative of x to the n plus 1 is n plus 1 times x to the n. Now, when we bring the n plus 1 to the other side, and when we exclude n equal to minus 1, then the n plus 1 becomes 0, which we don't like. The power rule tells us that an antiderivative of x to the n is x to the n plus 1 divided by n plus 1. Or this plus any constant. I would leave out the constants here. And so on. The derivative of the logarithm is 1 over x, so the antiderivative of 1 over x is the logarithm of x, or the logarithm of the absolute value of x, if you allow x to be negative. The exponential function, at the time we found the exponential function is its own derivative. Reading this backwards now gives the exponential function is its own antiderivative. Or more generally, the derivative of b to the x was ln b times b to the x, bringing the ln b across. Now this rule reads an antiderivative of b to the x is b to the x divided by ln b. The derivative of the sine function is the cosine. Reading it backwards, an antiderivative of the cosine x is sine x. An antiderivative of sine x is minus cosine x. And then we had the derivative of tan x is sec square x. Reading this backwards, an antiderivative of sec square x is tan x. Sec x in turn has derivative sec x times tan x. So an antiderivative of sec x times tan x is sec x. And then we found derivatives of inverse trigonometric functions. The derivative of the inverse sine of x was 1 over the square root of 1 minus x squared. So now we conclude that an antiderivative of 1 over the square root of 1 minus x squared is the inverse sine of x, and similarly for the inverse tan, an antiderivative of 1 over 1 plus x squared is the inverse tan of x, because the derivative of the inverse tan we found was 1 over 1 plus x squared. So there is the things we know about finding derivatives can be used to go backwards to find the function that this function is a derivative of. To finish this off, let's look at a specific example in relation to the question we asked at the beginning. Can you tell the position of a moving particle from its velocity? Just recapturing, if a particle moves along a straight line with position function s of t, then its velocity v of t is the derivative of the position function s of t. That now makes s of t an antiderivative of the velocity v of t. Moreover, the acceleration of the particle a of t is the derivative of the velocity function v prime of t, and that makes the velocity now v of t an antiderivative of the acceleration a of t. In practice, here we're given a particle that moves in a straight line with acceleration function a of t being 6t plus 4, with an initial velocity v of 0 being minus 9 centimeters per second, and an initial displacement s of 0 being 9 centimeters. Let's find its position function s of t. How do we do this? Well, we're given the acceleration function, and maybe next up is the velocity as an antiderivative of the acceleration. So using information from the table on the previous slide, the antiderivative of a sum is the sum of the antiderivatives, and then we have the antiderivative of t is half of t squared. The antiderivative of what t to the power 0, say, is t divided by 1, and then all these antiderivatives differ by a possible constant, which we just called capital C here. So taking all this together, an antiderivative of the acceleration function can be described as 6 times t squared over 2 plus 4 times t plus c, which simplifies to 3t squared plus 4t plus c. Now we know that the velocity at time 0 is minus 6. So this function v of t, when 0 is substituted for t, should give minus 6. And that's only possible if we set this constant c to minus 6. But in doing so, we now have completely described the velocity function v of t as 3t squared plus 4t minus 6. That's using the acceleration function, the fact that the velocity is an antiderivative, and one value of the velocity function to compute, to find the velocity function completely. And this we can do again. Now looking at antiderivatives of the velocity, which is the derivative of the position function, using the same rules. The antiderivative of a sum is the sum of the antiderivatives, so we do this term by term. 3t squared by the antiderivative power rule, and we found this earlier. An antiderivative of t squared is t cubed over 3, so this gives a contribution of 3t cubed over 3 plus 4 times an antiderivative of t, which would be t squared over 2, minus 6 times an antiderivative of t to the power 0, which you don't see since it's equal to 1, gives minus 6t plus this constant, say d, by which all these antiderivatives only differ. So this simplifies to t cubed plus 2t squared minus 6t plus d as a formula for the position function s of t that now involves an unknown parameter d. However, we're also given the information that s evaluated at 0 is 9, so this formula, when 0 is substituted for t, should become 9, and that's only possible if we set this d value equal to 9. So s of t becomes t cubed plus 2t squared minus 6t plus 9. That's how antiderivatives can be used to build up this model step by step. That's it for now. Next week we're going to look at exponential growth and exponential decay in pandemic times.